Bienvenue aux deuxième session pour les conférences des lauréats de l'ACP. Welcome everybody for the second session of the medal talks by the medal winners of the CAP. So we have the second talk of the afternoon, and it is Gordon Ball from TRIUMF, who has won the Vogt Medal. Gordon did his undergraduate degree at the University of Alberta, just like me, however, in chemistry, I guess. And then University of California, Berkeley, also in nuclear chemistry, his PhD. He has been a research scientist at Chalk River National Laboratory, and there he pursued broad accelerator-based research program in basic and applied nuclear and atomic physics. He was there from 1968 to 1997. And in 1997, he joined TRIUMF as a senior research scientist, where he initiated the program in super-allowed beta-decay studies at Icesac. In 2000, he assumed the responsibility for coordinating the installation and reconfiguration of the 8 spectrometer for a vigorous program beta-decay studies at Icesac, and was also an active collaborator in the CFI Griffin project, which was funded from 2011. In 2007 and 2008, he was the TRIUMF-ISAC Science Group Leader and the TRIUMF Science Division Head from 2009 to 2010. And in 2012, he has been an ISAC Researcher Emeritus. He will speak to us on super-allowed Fermi beta decay, studies at TRIUMF-ISAC, testing CVC and CKM Unitarity. Please go ahead and share your screen, Gordon.
Well, thank you very much for the introduction. Today, I want to tell you something about the Superallowed Fermi beta decay program studies at Icesac, which began, as you just heard, when Icesac first started. Thank you for the award. It's really appreciated, and I like to share the recognition with all of my colleagues. In the standard model, the CKM matrix describes a unitary transformation between the weak interaction eigenstates and the quark mass eigenstates. And the first row of this matrix provides a demanding test, experimental test of unitarity. The VUD element, the first element in this row, is the responsibility of nuclear physics. In super-allowed beta decay studies, the beta decay FT values, or the transition strengths, are related by phase space times partial lifetime, inverse of the matrix element and the coupling constant. And for super-allowed Fermi, pure 0 plus to 0 plus, the matrix element is a simple ladder operator, and the coupling constant is the vector coupling constant. What we have to do is measure all those three quantities, Q-value, half-life, and branching ratio, with high precision. This shows you the data that for 14 transitions where they are in agreement within 2%. This is pretty good, considering that these values can vary by many orders of magnitude. However, you can see that the uncertainties are still quite small for these values, and they differ by many standard deviations. Life isn't so simple, and in fact, you have to apply a number of corrections to these FT values. These have really two forms. One are radiative corrections that result from radiative processes such as bremsstrahlung. They are some that are nucleus dependent and ones that are nucleus independent. In addition, we have this delta C here, which is the isospin symmetry breaking correction due to the charge dependent forces such as the Coulomb force. However, when we make all these corrections, this shows you a summary of the data taken in 2014. You can see now that the CVC hypothesis is verified at the level of 0.01%. We can also then relate this to the VUD element by the expression that the vector coupling constant over the Fermi coupling constant for muon decay is equal to VUD. Then through this equation here, we then end up with this value for VUD squared, which has an uncertainty of about 0.04%. This shows you the uncertainty of the quantity from the different correction factors. Largest is delta VR, and the second is the isospin symmetry breaking corrections. When it comes to unitarity, at that point in time in 2015, everything looked pretty good. Everything is unitary within the errors of 1 sigma on the different quantities when you put in the values from K on decay for the VUS, and β-Decay for VUB, which is a very small and not very dependent quantity. Okay, the Icesac program began in 1998. The goal of the program was to extend the studies to heavier nuclei. At the time, only 9 transitions were known. They're shown here on this side of the slide. And we also wanted to check the systematics and correct any unknown errors in the data. And you can see that there's been quite a lot of changes since that 20 years ago in the quantities and also in their uncertainties. We also want to check for the isobaric symmetry corrections, which can vary a lot depending upon which theory you're looking at. These 2 here I've circled are the 2 most popular, which follow the trend of the data best over the years. Icesac produces its beam in the isol technique, where we have a 500 MeV proton beam from the H- cyclotron impinging on a thick target, where it's coupled to a variety of ion sources, such as surface ion source, laser ion source, Febia ion source for gaseous species, accelerated up to about 60 kilovolt after extraction, and mass separated and sent upstairs to the Icesac floor. This area is the low energy area, which I will be discussing. This is where our facilities are located. There are accelerated areas for nuclear astrophysics and nuclear structure studies. And in addition, we have material science going on. So it's a big laboratory. When I went there, it was a big empty space in the hall, I can tell you. Okay, we've over the years developed equipment to measure all of these 3 quantities. The first I'll tell you about is GPS. That was the first beta counting facility on the floor at Icesac. That was later followed by 8-pi spectrometer that was brought in and reconfigured for beta-decay studies. You can do branching ratios and lifetime measurements with that. Then we have replaced this with a much more modern spectrometer called Griffin, and that has really changed the game too. You'll see that later. There also, we have the Titan facility, which has measured 2 of the super-allowed emitters, and there's been 1 charge state radius measurement for rubidium. This slide summarizes all of the measurements that we've done so far in the past 20 years, I guess now, and there's actually about 22 different measurements. The ones in green are actually mirror nuclei. They're not super-allowed transitions, but they can be used for that purpose, but I won't be talking about these ones in this talk today. The ones in blue are data that have yet to be completed in the analysis stage. The first facility on the floor was the GPS facility. This is not a very early picture because when it was on the floor, it was just a short beamline stub here. And since it was installed, we've measured super-allowed branching ratios for 8 of these emitters with the precisions better than 0.05%. We have an implantation here stage in a differentially pumped, doubly differentially pumped. We implant at this point, move the tape system, which travels at 5 meters per second, place the sample in, tie a 4-pi gas counter, and count it for about 25 half-lives, and repeat the cycle and over again, depending on how many counts we wish to have in a given run. And we have to control the time of the whole thing with a frequency generator. And another important thing is a fixed extendable dead time, non-extendable dead time for every event, so that we can dead time correct the data before fitting it, and we don't have any rate dependent effects on the half-life from that. The first measurement, the first precision measurement that was made for this was a high precision measurement of the super-allowed beta-decay of rubidium-74. In this case, we had a beam of about 4,000 rubidium ions. It has a very short half-life of about 65 milliseconds, and it took us about 1 half-life to move the sample out. So you don't get too many counts per run, but you can make a lot of runs because they only take a few seconds. The net result of this measurement, this is many different runs we had, which shows that we got consistency. We change the parameters from time to time and see that we get a consistent, there's no systematic errors. This result was a factor of 20 improvement in the previous value. Person here, Sean Bishop, was a student who helped me at the time when we didn't have too many bodies around on the floor to help. He was and I worked together pretty hard on the floor to put this experiment in place. He later went on to do a measurement at Dragon, get his PhD there, and then he's now at Technical University at Munich. And about a year ago, he was diagnosed with a glioblastoma brain tumor. And his courage and his positive attitude over the past 12 months has been and really been inspiring to me and to many other of my colleagues. And I'm especially thinking of him at this time. This shows you a summary of the lifetimes we've measured. These are the 8 transitions we've measured, and we have the most precise measurement in every single case here. This shows a history with time of the GPS results where we set world records 4 different times for a single measurement. I obviously can't talk about all this data, but I will choose the one measurement here, the latest one, carbon-10. And this was done more recently than the other ones, and it was done after the facility had been moved to a new location downstream of the 8-pi spectrometer, which I'll talk about later, and Griffin is upstream. And this position allows us to actually do simultaneous measurements with gamma counting at a spectrometer and beta counting at GPS. In this case, we had a nickel oxide target and a Febide source to produce the beams of interest. We had a carbon beam and a CO beam, which was carbon-10, oxygen-16. This shows you the beta counting data here. Now we have much better statistics, many more counts, 10 to the 6. This is all the data taken for one dwell time. And we also noticed a contaminant in this case, which was actually, we believe it was N13, which has about the same mass difference as CO. And you can see that's the green component here. Fortunately, that has a very long half-life, so it didn't affect the measurements, but we have to include it to get the precision we need. Here's about 85 different runs, again, varying all these different parameters. I'll show you that in this slide. Here's the systematics that we get by varying various parameters, such as the counter voltage, the threshold, and so on. In this particular experiment, we didn't see any variation systematically here. All these different sets are chi-squares less than 1, so we didn't add any uncertainty. So this precision on this measurement is about 0.009%. That's about the limit of this technique, I would say. We also did gamma counting with the 8-pi. Here we can gate on a 700 kilovolt gamma ray and follow the decay, vary the things here. In this case, pileup corrections are very important. We had done these before. This was led by Gwen Grenier, who's now a professor at University of Regina, was a student at the time. This is the measurement we get here. Its precision is about 0.04%. This is an ideogram that shows you the data that we got at the top here, the 8-pi and beta, and the lifetime in this case was an improvement of a factor of 3. The weak scalar current can also be used to contribute to 0 plus decay, where it would introduce a term proportional to 1 over the average energy of the decay. So instead of having a constant, you have this extra term in here, which this is the Fiertz interference term, which gives you the ratio of scalar to vector currents. When we fit the data, the ones at the lightest nuclei, like carbon-10 and oxygen, they have the lowest Q values. So they are the ones most sensitive to this measurement. When fitting this data, we have established that the ratio of scalar to vector was a value of plus 0.009 with an error of 0.0011. And this was the first reduction in this upper limit in over 10 years. Now going on to the branching ratio measurements that we want to study with the spectrometer. In about 2000, there was a paper came out by Hardy and Towner, which said that it would be very difficult to measure the branching ratios for these heavy systems because you can produce a large number of 1+ states, which will decay down here to the ground state. And you'd never see them because they were very weak. However, in fact, they said new techniques must be developed to get the reliable numbers. However, we did set up an experiment in 2002. This was led by Ed Skyner and his postdoc, Andreas Pikacek from LSU. It had a germanium detector and 2 plastic decounters and a couple of silicon counters, because in this case, the second excited state is a 0+ state that has an E0 transition in it. The key to the measurement was that, in fact, the low-lying states, the 0+ and 2+ states, they act as collector states. And so we get the missing component is the ground state transitions from these high-lying levels. And we can get some idea, an estimate of that from from theory. And when we do that, we got a value that was about a precision of 0.1%. And we only saw one plus state at that time. The 8-pi spectrometer was moved to TRIUMF in 2000 for a program in beta decay studies. We reconfigured it. We close packed the germaniums and collimated them, put in Delrin absorbers for bremsstrahlens. We built a scepter detector with 20 element plastic to do the beta detection. And then we have this tape system here, which tapes a continuous loop into a box so we can move the sample behind a lead wall for the long-lived activities. And both of these components were designed and built by Ed Steiner. This shows some of the pictures in the early days when we were just doing the construction with the group. And at this time, Carl Svensson got a position at the University of Guelph, and our group started to grow. And this shows the happy group when we got our first beam unit spectrometer in 2002. Here's some data we took for the rubidium-74, where we're going to try and improve it by a factor of 3 using this same technique I just talked about. You can see some examples of the spectra here, and here's the gamma ray spectra that has far more details in it than previously. There's an electron spectrum to measure the E0 transition. In this case, we had about 10 to the 9 decay events. And these are the ground state transitions that we saw: 57 gamma rays, 9 1+ states, and many, many more 0+ states. The number is about 0.4% there. Now, how are we going to determine what's missing? Well, these are these states. This is what we want to determine, the ground state missing component. Well, we actually see the 2+ decay of those states because they feed the low-lying states. And by looking at the intensity of these feeding in and feeding out, we can determine that quantity is about 0.1%. Then if we use the theory and experiment on the 1+ states we do see to establish the branching ratio of the two, and that comes out to be roughly 1/3, we can then estimate the missing fraction. And this then gives us the required number, which is accurate to a precision of 0.031%. This is the current uncertainty in this quantity. Okay, we did similar measurements at GPS and 8-pi for gallium-62. In this case, we got very good precision, and it was equal to the precision of the well-known cases. And we can then use this to try and see if we assume CVC, how good the model is for the different theories. And you can see here that the gallium and rubidium agree very well in this model. And in this case, one of them is not. That was the first beam, laser beam from Icesac. Okay, in 2015, we have the Griffin Spectrometer. This has revolutionized things. You can see here the difference in the data set that we get from Griffin for the gallium-62 decay that I was just talking about when we set a gate on the lowest transition. A few counts here, many high statistics here. That's due to a 300-fold increase in gamma-gamma efficiency with these large Clover detectors. Again, we identified many, many levels, and now we've improved this branching ratio for gallium-62 to 0.003%. More importantly, we also were able to confirm by using angular correlations that the spin of the first 2 excited states here, and that was important because we can also measure their intensities. And when we measure their intensities and sum up the intensities of the 0+ states, there's a formula here that relates the sum of these intensities in mixing to this parameter delta C1, which is calculated from theory. We get a number here which is extremely different from theory. So normally when we make these measurements, we're subtracting this quantity 0.27. If we use the theory value of 0.1, that would change the value we get significantly. So there's a real need for better calculations of these theories that aren't restricted to the nickel core. This is the present state now in 2020. Nothing much has changed except that the theoretical corrections have now changed. So recently there's been recalculations of this radiative correction delta NS. That's resulted in a factor of 3 increase here to 1.85. You can see down here this quantity was not even there, and that is now the largest uncertainty in FT. Furthermore, the radiative corrections delta R, which are nucleus independent, have also changed, and they cause a shift of 2 sigma in VUD. And the result of that, you can see over on this corner slide here, where from 2015 to 2020, the uncertainty has now gone up to 0.6, and the largest of this uncertainty is coming from this nuclear structure component, and the uncertainty in this other quantity has gone down. More importantly, now this leads to a deviation of 2 sigma in unitarity. This is the largest deviation, I would say, in over a decade. There's still some residual and discrepancy in VUS from 2 different kaon decays, 2 lepton, 3 lepton, but these won't account for the 2 sigma deviation. We need to have reevaluation of this other correction, the delta R primed. We need again to scrutinize the models for isosymmetry breaking. The future Icesac program will make the new measurements more important than ever. This outlines our program, and that's pretty well much what I have to say. Here's a bunch of pictures of the group, a lot of students working on all the equipment. Here's another set with various colleagues in it. And in the course of these experiments, there were something like 150 different postdoc students and collaborators from Canada and all over the world. The ones in color are highlighted. These are all the TRIUMF ones, and they're there for where they were at the Institute at the time. And then we have super-allowed collaborators from other institutions, 3 pages of them. And finally, I would like to thank TRIUMF and the CAP for this medal, and thank all those who supported my nomination, and acknowledge the funding support from NSERC and the CFI and its funding partners. And thank you very much. It's been a privilege to be part of this wonderful journey for the past 23 years.